Good afternoon. Today's lecture is about a very important topic in machine learning is the data pre-processing and data quality. Okay. So we can see here that data quality is essential for good machine learning algorithms. So this slide now has some information to say. Okay. Now, in the second slide, the same, repeated, but maybe with different color. Okay. Third slide, also the same. Data quality is essential for, but with just smaller size. The same, but slightly oriented. The same, but many of them. So actually, you got information from the first slide, but the repetition is almost they just junk. So they don't have extra information to give, unless there is something hidden in the code or in the colors. If we try to send another message in color, for example, like some secret code or something, it might have, like in that case, information. Otherwise, if it's just different representation of the data, so actually we just lose storage, we lose time, we lose processing for nothing, because we just repeat the same kind of information. In that sense, machine learning, to be effective, it needs high quality data. Okay, so in this lecture today, we will talk about data quality and data pre-processing, introduction to dimensional reduction in data, subset selection, principal component analysis, feature embedding, multidimensional scaling, linear discrimination or discriminant analysis, and locally linear embedding, and then we give some exercises. Maybe not all will be covered today, but we try to do as much as we can. Okay. Data quality is nowadays is very, very important, because actually we have extremely large availability of data. And also we have data streaming, for example, over Internet of Things, IoT, videos, social media, and others. So data volumes increases in exponential rate. I read in one article that all data in universe, on Earth, is almost doubled every 2 years. So you can see how much data that we have. Every 2 years, the whole data in the world are doubled every 2 years. So you can see that maybe within 5 years, how much it will be, like 2 times 2 times 2 times 2, and so on. So there are many opportunities due to this availability of huge data, but at the same time we have many challenges. For example, how to handle big data volumes. For example, if you want to build some machine algorithm to handle like 1 trillion terabyte of data, it is huge, very huge, extremely huge. And so handling this big data volume is very big challenge, and we should look to this data and how to reduce the size of data without losing big information. Another challenge is the heterogeneous data sources. So we have data sources, as I said, from IoT, like Internet of Things. We might have videos type of data. We have context or text or whatever. So we have many data in different structure, and many of this data are unstructured. So this is one of the challenges in data management. We have data duplications. So many data are duplicated in different forms, as we saw in the beginning of this slide. So the same data, but it came from different orientation or sizes or whatever. Also, we have a lot of junk and rubbish data inside. So we have a lot of challenges how to deal with data. So it is very critical to have well-designed and sustainable data strategy in order to clean data and to guarantee successful machine learning applications. Actually, I read in one article also that about 25% of some companies loss in their revenue because of the like bad data. Because of bad data, the losses can reach to up to 25% of the revenue. So it is very critical topic. In general, garbage or rubbish data for machine learning will produce rubbish models. So garbage in, garbage out, or rubbish in, rubbish out. So it is very important that we guarantee the quality of our data in order to guarantee good quality machine learning or artificial intelligence applications. If you like to build like machine learning algorithm to predict the prices of cars, that as the same example that we saw before. If the data that you collected was just random data, it was not reflecting the real situation, just random numbers. So of course, the machine will learn something wrong. And it is not applicable at all because it is rubbish data, and then the algorithm that you will get is just rubbish algorithm. It is not useful for anything. So it is very important to have good data quality for the machine learning. It is the same here, the same example that I started with. So for example here, but in form of numbers. So if you have two rows, like two attributes and one output, so 1, 2, 3, 0.1, 0.2, 0.3, 3, 6, 9, actually those three types are the same, but just scaling. Because here if you multiply it by 0.1, you get this one. If you multiply it by 10, then you get some other number, or you multiply by 3, you get the same number, the same set. So it is useless. And sometimes you have huge data, but this huge data, most of them is just duplications or redundant data. So it is very important to think how to reduce the size of data. Very large redundancy will complicate the learning process because you have large data, and also introduces numerical errors because many of our machine learning algorithms, as we saw last lecture, based on inverse of some matrix, for example. And if you have like a repetition or high correlated data, then you will have singular or ill-conditioned matrix, which cannot be inversed with high reliability. So data reduction is based on removing this redundant data from our data. So this is the topic, actually the main topic of today's lecture, because there are some other topics related to data quality, but they are more related to computer science. For example, like how to improve the structure of the data, for example. Or unstructured data, how to make them structured data, and so on. Okay. Yes. Most of the our data, actually, just to remind you about one kind of the structure of our data that we have attributes x1, x2 until xd. This is the dimension of our data, and then we have outputs. Can be, for example, y1 and y2 and whatever, but let us talk about one output. And this is our data. So, and we have here like first sample, second sample. So we can put the sample number up. So this is 1, and this can be x1 but 2. So it is for the second sample. Okay, and this is the output, the second output, and then we might have up to n samples. And xd n. So this is our data. Sorry, we have n samples. So we have n samples. As more data we have, usually it is good. If under important condition that every data here or every row add some new information. There is no redundant information or no repetition for the same data. And also, the dimension of data. So also we need the dimension to be like as low correlated as possible. If there is one dimension, that it is just representing, for example, if the third one, this one, is 2x2, is just double of x2. So 2x2, 1, 2x2, 2, and so on. So this will introduce errors actually when you compute the covariance matrix of this data, because this is just a repetition for the second data. So we should be able to remove it, or we should remove it. The problem here that in the practical data, usually we don't see them in this simple way. So we can see, for example, here x2 or x3 can be some combination of the other elements, which can be very hard to see it directly. But we will study how to find those highly correlated inputs and remove them from the data that we have. This example here, if we have like 10,000 inputs of data sets, and each data set consists of 100 attributes, then here we will have about 1 mega data units that we need to teach our machine learning algorithm. If you found, based on some reduction technique, that 70 attributes were just linearly related to the other 30, so it means that you can reduce them that much. 70 times 10,000, that it can be removed from your data, which can reduce a lot the processing, computation, and also the complication of the learning process. And also actually you will increase the ability to interpret your data, because as you have much more dimensions, it becomes more complicated to interpret the result, because you will have highly complicated or complex algorithm, which can sometimes hard to interpret. Okay. In the data reduction, we have mainly two methods. One method is named feature selection, and the other method is named feature extraction. The feature selection based on looking to this data, and then we look to the most important. For example, if we have D inputs, like this one, so we are looking for K, the most K important dimension out of D. So we are looking for the most K. Of course, K should be less than D. So we are looking for the most important K dimensions for our data, and then we omit the rest. So in that case, D minus K of the dimensions are just thrown away from the data, and we take only K inputs. We are looking for K inputs out of this data. We will see how to do it. This is called the feature selection. So we select some features, because those are features actually, or attributes. So we are looking for the most important features that it will affect our result. The second method, which is very famous, is called feature extraction. The feature extraction, we also looking for the K dimensions, which is less than D, but we don't actually throw away any of those dimensions. We make some projection, some linear projection for this data. For example, here we have D elements. So if we multiply this by, for example, in the linear projection, it means that we multiply it in another vector. So the other vector that we multiply, it will generate, for example, if we have W, and W is like K times D, and then we multiply this D dimensions. This is X, it has D, it is vector D. So when you multiply them, of course it is D by 1. When you multiply them, you will get a new vector with K plus 1. So this K, which should be less than D, is smaller than D, but at the same time, it is a linear combinations between those inputs where we can reduce the data size in that sense. So this is called the feature extraction. It is the principal component analysis, actually, that we will describe today. This is the principal component analysis. Okay. Actually, the feature extraction, we have two kinds of feature extraction. The first is unsupervised, so we don't need to look to the output. We just look to the data, and then we reduce the size of the data by using principal component analysis by projecting this data into lower or smaller size or smaller dimension. The second kind is called linear discriminant analysis, and in that case, we take into account also the outcomes, the outputs, especially in the classifications. For example, if this is class C1 and this is class C1 and this is class C2, C1 and C2, then we take into account also the classification in order to find the optimum or the optimal reduction in the data. Those are the main principal techniques, but of course there are many techniques in the literature. Most of them, they are derived from those two principal or simple techniques, the PCA, the principal component analysis, and the linear discriminant analysis. But there are some other techniques which some of them they are non-linear techniques, or they define different way to calculate the distance between the element and the neighbor element that we consider them the same. We will talk about these later. Okay, let us start with the subset selection, where we use the feature selection, the first one, the feature selection method. One method is called subset selection. What is the subset selection? It is a very simple method, and it looks very also intuitive method. X2, X3, 1, and X3, 2, and so on. Okay. Yes. Then we have here our outcomes, which is Y, and this is the inputs. So we have here Y1, Y2, and until Yn. Yes. This method is based on this procedure. First, we can make the learning or the classification or the regression of the data and the output. Okay. We complete with all data that we have. For example, we have N data. As we explained before, we can divide them into training set, training, and also validation. Okay? We divide the data into training and validation. Now we make the training for all data that we have, and then we validate the data and we complete the learning in that sense until we got good result. Okay, so now over the validation, we have achieved some error value over this validation. For example, let's say that the error over validation is, let's say, 0.01, for example, the average error. Okay, now what you do, simply you come and you remove X1. You remove all X1. This feature, you remove it from the data. You take off this X1. And then you repeat again the same learning. So you repeat the same learning with the data, but without, you exclude X1. And you take the other from X2 until XD. Okay? Then you check the error over the validation. If you found the error is almost the same performance, or it might be like slightly larger, like for example 0.011 or something like that. So the error has been slightly increased, or this is the same error, or sometimes the error can be even less because this extra data, it might be just noisy or just junk data, which complicates the learning and didn't achieve the good error because of it. So in that case, what we do, okay, this is X1 has been removed now from our data. It means that this feature doesn't have big impact over the modeling. Now we start to remove x2. Assume that when you removed x2 and you repeated the same learning process again, the error over the validation becomes like, let's say, becomes like 10. What it means that x2 is critical, it's very important for our data. So the information carried by the feature x2 is extremely important, so it shouldn't be removed. Okay? Now we repeat with x3 and so on. Once we complete them, then we start to remove 2 by 2. For example, if you have, like, let's say you have 3 data, like x1, x2, x3. You made the learning, because we have the output 1. We made the learning, then we remove x1 alone. We repeat the learning, we check. Then we remove x2 alone. We can bring back x1, and then we make x2 alone. Then we repeat with x3 alone. Now it means that we have the first learning process, the second learning process, the third, the fourth. Then we come and we remove x1 and x2. You know, sometimes x1 alone is important, okay, and x2 alone is important in some data, but together in some data they cancel each other. So we start to remove x1 and x2 together, and then we remove x1 and x3 together, okay, and finally we remove x2 and x3. So what it means that we have one learning process, second, third, fourth, fifth, sixth, seven times that we need to repeat the learning process. So simply it is 2 to the power d minus 1. So actually it can consume a lot of time to do it in this way. For example, if you have 100 dimensions, it is 2 to the power 100, which is very, very huge number. So maybe a supercomputer will not be able to do it unless it takes like decades, especially if you have like n is very, very large number. So in that case, it means that we need a lot of time for this subset selection. There's another method. This one is called backward. So we started with all of them and then we start to remove them one by one. There's another method. It is the same, but it's called forward. Forward selection. It means that we start with 0, nothing. Of course, nothing, we don't have any input, but start with just, we add one by one. We add first the first feature, and we check what is the error. Then we add the first alone, then the second alone, the third, until the D1. Then we add them 2 by 2, 3 by 3, 4 by 4, until we complete all of them. This is called forward method. But as I said, usually like checking all situation can be time consuming and requires a lot of time, which is not needed in many applications. So there are some heuristic methods that we can do. Most of the methods based mainly to remove 1 or 2 out of D. So we start by removing 1 by 1, and then maybe 2. Once we remove the one which has the least effect or the least impact of our data, then we start to check another one. So we don't remove like 2 by 2 and search for all possible combinations. No, but we can remove just 1 by 1, and then until we reach to the most compact size of data. So this is one method, one simple method for the feature selection. As I said, this is the backward and the forward. So as I said, this is mathematical representation. So in case that if you use the forward selection, so every time you start with empty with the forward, then you start adding them one by one and checking the error every time. And in the backward, it is the reverse. You start with all data, and then you compute the error when you remove like the features one by one, and then you just remove the one which has the minimum impact on your data. So this method is important. Actually, one important feature for this method that also in the interpretation of the model. For example, if you are working with let's say voice recognition. In the voice recognition, machine learning of voice recognition. Okay. So we have the voice signal, okay, and now we like to extract features from this voice signal in order to be able to build our like machine learning to recognize like voice or words or whatever. So what we can do here, one method is based on wavelet transform. Wavelet transform can be represented by, for example, it is called filter banks, where you can divide the data into low pass and high pass. So this is, for example, low pass filter. It takes only the low frequency, and this is high pass filter. You take only the high frequency. By the way, this can be also applied the same for like if you have a stock market or in business or whatever. So, and now you can also divide them. The high frequency part, it is also like two, like low pass filter and high pass filter, and the same for the second one. This is called frequency or filter banks approach, high pass filter, and so on. Okay, so in that case, you will end it by some features. So those are the features that we have at the end. So we can call them like x1, x2, x3, x4, and so on. And now during the learning, for example, if our learning process is based, for example, to maybe recognize a word, or maybe recognize the speaker, who is the speaker, because we know that every speaker, he has his voice thumb there. Okay. Now we for the certain speaker that he talks, and then we during the learning, maybe using neural networks or maybe using some of the parametric classifications that as we have seen before, we start with those features for every speaker. For example, this is Muhammad, this is Adil, this is Mike, this is and so on. And then based on the learning, we have sometimes like 30 band, subband, or maybe you have 100 subbands. And some of those subbands, for example, this is x1, and this is x2, and this is x3, and so on, some of those subbands, they might not have that big impact over the learning for all speakers, okay? Because when we remove them, we found that the machine is still able to recognize people, even without x3. Why I should include it? And actually, if I didn't include x3 for it, maybe x3, maybe also, let's say x7, maybe also there is x9. So if we decided not to include like 20 of those features, then we don't need to collect this data. So we save time, we save money, we save computation. So it is important. And also, look into this x1, for example, if x1 has the highest impact of all users, then we can come to some interpretation, some physical interpretation to say, for example, if x1 gives the frequencies, just example, let's say between 800 to 900 hertz. For example, in this x1, which gives this band, was the most important feature in this data. So this we come to some interpretation that to say this is a behavior that 800 to 900 hertz is the frequency band which carries the thumb of the speaker, or the most important one at least. So this is the way that reduction in the size will lead also to it becomes much easier to interpret the result and to have some explanation over the obtained results. Yes. Okay, we have this example now. I generated these numbers from x1 to x4 as input, and we have the output y. Then I used the function of artificial neural networks math which is already in the model, and those are 30 inputs. So we used 15 of them for training and the other 15 for validation. And this result shows that when we include all inputs from x1 to x4 and also the output, this is the validation error. So the average error over the validation was only 0.01, which means that the network was able to capture the relation between 4 inputs and the output. And this is the error performance during the training. Okay. Now, what I did, I just removed x1. So I removed x1 from the training, and I repeated the same training again. However, the average error over the validation becomes 1.06. So it is about 100 times than the average error if I include all data. So this means that x1 is critical and cannot be removed. And this was the error during the training. Okay. What I did, I repeat x1 again to the data, and then I removed x2. When I removed x2, actually I obtained almost the same result, 0.01 of the error. Then x2 doesn't have important information for this training process, at least within the available like set of data. It might have some important, but not for the data that we have. It means that x2 it can be removed from our data. Then I repeated with removing of x3, but again we have large error, which means that x3 is important, and we can repeat the same process in this way. So that's all about the feature selection method. Now we come to the feature like extraction. Feature extraction mainly is based on the projection principle. So the idea here that if we take one input, this is x input, you can see that x input here is real numbers, and the dimension is n times d. Just to keep you tracking what we do in the slide, so it is good to have them also with a simple example on the board. So we have here, I will assume that only 4 data, okay? So this makes easier for you to understand what I'm doing. So here, for example, x1 and x2 and x3 and x4. Remember that principal component analysis is unsupervised method. It means that I don't need to know the output y. I don't need to know the output y. We can reduce the size without even looking to the output. So now we are looking only to the available data here. Okay, how many here? D here equal to 4, because the dimension of data is 4. So we have 4 features, okay, or 4 attributes. N is the number of samples. For example, if x1 is the salary, average salary, monthly salary, x2 is the gender, and x3, for example, is the age, okay, and x4 is the weight, the best. So we assume that this data that we are looking for something outcome of this available data, and those people are independent. So we have, for example, for this guy that his salary is 7,000. Okay, let us put the number is in thousand, in 1,000 euro. Okay, so it is 7,000. His gender may be 1. We can say the gender is 1 and minus 1. And x3 is the age, maybe 60. And the weight, maybe 65. And this maybe, let's say 10,000 minus 1 and 59 and maybe 50 age. And this guy maybe is 5,000. And the gender is maybe 1, and the age is 40, and the weight is maybe 105, and so on. Okay, so now this n is the number of available data. Assume that we have, this is the customer C1 or 1, customer 2, customer 3, until customer 50. So we have 50 customer, we have D equal to 4 is the dimensions of those, or the number of features. In those slides, we are going to explain in details the principal component analysis. Principal component analysis is one of the most important techniques in actually in many applications, not only in this data reduction, but it has many other applications as well. Okay, now we have this. So the X now belongs to, as it is shown here, it is real numbers, okay, and the dimension is n. N means the number of rows times D. So in this case, we have 50 times 4. So this is the dimension of our data. So we have 50 rows. Rows means that the inputs, and then we have 4 features. Okay. What happens if you multiply all this by a weight, and this weight, W, the dimension of weight is D times 1. Okay, it's D times 1. So if we take the transpose, so if we take the transpose of D, of this W, so W transpose means that 1 times D times X transpose, which is D times N. So as you know that from the multiplication of matrices or vectors, so they are the same, so the result will be, the vector will be 1 times N. So what happened? If you multiply vector is 1 by D. 1 by D means that W1, W2, W3, W4, in this case, in this example, multiply this matrix. This matrix contains, as you can see here, we have 4 inputs, okay, and we have 100 rows. But because we take the transpose, so this becomes the input. So we have like 7, 1, 60, 65, because we take the transpose. The second column will be 10, minus 1, 1, and so on, and so on. So in that case, we will have the repetition of this one. Okay, so the second one, also, this is 10, minus 1, and 59, sorry, 59, and 50, okay, and so on. So we will have here, this will be 1 row by 4 elements. This one will be 4 columns by 100 columns, 4 rows by 100 columns. The result will be 1 by 100. 1 by 100. So Z equal to 1 element by 100. What it means? It means that I projected this 100 by 4 into only 1 row is 1 by 100. So this is 1 by 100. So this is the projection. The projection that all of them, that every dimension, 4 dimension, are projected to only one number. Every dimension is projected to only 1 number. Okay, by using this projection W1. Okay. Now, if I make the projection again with W2, then I will have another Z1. I will have Z2, only 1 by 100, and Z3, and so on. Okay. What is the purpose here? The first question that we should think about, how to select W1. The idea here, they said you should select W1 in order to make this matrix as scattered as possible. Why? If you project all this matrix into a number, let's say, if we have 2 dimensions, we have now 2 dimensions matrix, okay, and if you project it to only 1 number, all these elements, only 1 number, and I want this number because now we will have also the same number of samples. So if all samples are very close to each other, maybe. So when we have all data are very close to each other, so that the covariance is very small, or the variance of data is very small, we might lose a lot of information. So in order to keep or to maximize the information, what we need to after the projection to have the data as scattered as possible. So if they are small, we need to increase the distance between them. Okay? So the idea here, our idea, is how to find the optimum W that maximize the covariance after projection. The covariance of what? The covariance of Z. After the projection, we have the vector Z. So the idea here that, okay, what is the covariance of Z? The covariance of Z is equal to, because here we have like Z is, as I said, it is 1 by 100, so it is 1 by 100. So if you multiply it by Z transpose, it will be 100 by 1. Then so the multiplication, it gives you a single number. We need this single number to be maximum, to be as maximum as possible. Okay, so then we multiply Z1 by Z1 transpose. And we have the covariance of X is Z, or Z, as we explained in the previous part. Then the variance of Z1, okay, we can compute it easily actually. The variance of Z1 is the expected value of Z times Z transpose. So it is the expected value of Z. What is Z? We know that Z is equal to W1 transpose times X transpose and times Z transpose. Z transpose means that you just swap them. So you have that X times W1. Okay, W is a fixed number, so X is the one that you can take the expectation because it's the random process that you have, or random variable. So it is W1 transpose times the expected value of X transpose times X times W1. And this equal to W1 transpose, the expected value of X transpose times X is the covariance Z of X times W1. So this is the result that we have. This is the variance of Z1. The value of Z1 is a single number. We need this single number to be as maximum as possible, in order to have much higher information. You know that increasing variance, what is the meaning of increasing variance? Increasing variance means increasing the randomness in data. Okay, if you have the variance equal to 0, then you have a single number. When you have variance equal to 0, maybe you have, let's say, the number is 5. What is the next number? 5. The next number, 5. It is always 5. So it doesn't have information. You have information only the first time. It is 5. After that, it's just repetition. So as we increase the variance, it means that we have more predictability, that we need to know the next number, what is it. So there's more information coming. Actually, this is the main concept of the information theory, that the information content for a single event is related to log 1 times the probability, divided by the probability of that event. So if the probability of that event becomes 1 means that it is sure, there is no information. Log 1 equal to 0, so there is no information. As B becomes smaller, the information content in that event becomes higher. So this is actually at least the mathematical concept that we need to maximize the variance. Maximizing the variance, here we assume the mean is 0. So maximize the variance means that we maximize the scattering of the data, and then more information will be contained in that projection. So the main task that we maximize this variance. Okay. What we need to maximize the variance, but at the same time, we should normalize our vector, because here our vector is only for the direction of projection, not to the scale, because the scale can be anything actually. So the scale doesn't matter. So in that sense, we put W1 transpose times W1 equal to 1 to guarantee that it is only the scale. It is only the direction that we are looking, not to the scale. As we said, every vector, we explained this before, that every vector, it has magnitude and direction. Before we give the break, just to mention the formulation here, what we need to do, if you remember from part 1, for the Lagrange multiplier, because we need to maximize the variance of Z, which is, we said that is W1, it is W1 transpose times the covariance of our data, the covariance here of data, times W1. That's what we need to maximize. Subject to what? Subject to that we have constraint here. The constraint here, the magnitude of W1 equal to 1. That's what we need to do. Okay? Magnitude of W1 equal to 1. Of course, the magnitude of W1 is nothing but, as it is given here, it is the magnitude of W1 is equal to W1 transpose times W1. Okay? So we need here W1 transpose times W1 equal to 1. Okay? Then by using Lagrange multiplier that explained before, that we need to maximize the unconcentrated version of this equation, which is W1 transpose times Z times W1, then minus alpha or lambda. This is the Lagrange multiplier of W1 transpose W1 minus 1. Minus 1. This is what we need to do. And this is easy to solve, as we will see after the break. And then we can find what is W1, and based on that, we can build our principal component analysis algorithm. Actually, once we build the algorithm, and I show you how to use PCA, those you don't need it to remember even, but at least to understand from where it comes. From where it comes, the PCA, but the application is very easy, and how to use it is also, we have like ready functions in every like programming package, as we will see after the break. Thank you. So we take 15 minutes as a break and we continue. Okay, we continue. So as I said before the break, that we need to maximize the variance of the projection. And also we need to guarantee the magnitude to be fixed. As we said that every vector, it has magnitude and direction. So now we are looking for the best direction of the projection, not the magnitude. The magnitude can be 1, can be 2, can be any number. It doesn't matter. So we don't want to make this number, because if we don't make this constraint, and we want to maximize, so we might end up with very large W. It can be infinity, because this will maximize this number. So, but by constraint here, the magnitude to be 1, so we have only one solution for this maximization problem. Okay, as we saw that maximization is that we take the derivative of this scalar, because this will be scalar with respect to a vector W1, and we explained this in part 2, how to make the differentiation, and differentiating this one, that we get this result, and then we have the result that the covariance of x, z, or z, times vector W1 should be alpha times W1. This is the result. This is the result. That Z is the covariance. And by the way, the dimension of this covariance Z is d by d. D by d. The dimension of Z is the dimension of Z is, yeah, and it is d by d. You can compute this Z, for example, in Octave by using this covariance of x. It gives you the covariance matrix d by d. Okay. Yes. If we look to this function, or to this relation, that matrix Z times vector W1, it gives some scalar times W1. The dimension here is d by d. The dimension here is d by 1. So the result will be d by 1. This is a scalar, 1 by 1. And this is also d by 1. Okay. Actually, this form is very known in mathematics or linear algebra, that this will be achieved only if alpha is an eigenvalue of the matrix Z or Z. In general, I give it maybe in not in Z and W, but in A matrix for any square matrix A times x vector x equal to alpha x, okay, then we call lambda as eigenvalue of A. And x in this case is the eigenvector, is the associated eigenvector. So lambda is called eigenvalue. It is a scalar, is a number, and this vector is called eigenvector associated with this eigenvalue. Why? Because if you have the matrix like dimension is n by n, then you might have I. So you might have n different eigenvalue under some condition. I'm not going to in the details of this, but in that case, lambda I, it can be lambda 1, eigenvalue 1 with vector, eigenvector x1, lambda 2 with eigenvector x2, and so on until lambda n with eigenvector xn. Okay, so this is very general in linear algebra. In linear algebra, that for any matrix multiplied by vector, it gives scalar multiplied in the same vector, then this alpha is the eigenvalue and this W1 is the eigenvector. So actually this is very important result, that W1 should be eigenvector of the covariance matrix Z. Should be eigenvector of the matrix Z. But which one? Because as I said, if you have n-dimensional, in this case we have d-dimensional matrix D, so we have d different eigenvectors. Which one we should select? Which one of them we should select? Okay, now what we are looking to maximize, we said that we like to maximize W transpose times Z times W. This is what we are looking to maximize. Okay? Yeah. Now they said this, we want to maximize this one. Okay? Now they said that this result, that this is W1, they said that Z times W1 equal to alpha times W1. So we can take this and we replace it with alpha. Alpha is a scalar. So it becomes maximize alpha times W1 transpose times W1. But W1 transpose times W1 equal to 1. Then we should maximize alpha. We are looking to maximize alpha. It means that we should select the eigenvector which maximize or associated with the maximum eigenvalue. Because for any matrix we have, as I said, in this case we have d by d. It means that we have d eigenvalues. Okay, we select the eigenvector associated with that maximum eigenvalue. And when we do that, we have obtained the first component of the projection. Because now we build W1. W1 is the maximum, is the eigen vector associated with the maximum eigenvalue. Okay? The maximum eigenvalue. Now this is W1. It means that this is the first projection. Now we are looking for the second projection. The second projection, W2, the second principal component W2, should also maximize the variance as we did before. So also, we are looking now to W2, as we said, this is Z2 equal to W2 transpose times X transpose, as we did before, as is shown here. Then the variance of Z2 is equal to W2 times Z, okay, times W2 transpose, and we need the magnitude of W2 to be 1. This is one constraint. But now we need another constraint, that if you solve this function, you will get the same result as W1. Now we are looking for the second principal component, not the first. We have already found the first eigenvector. Now we are looking for the second eigenvector, which also maximize this variance. So what the other condition that we should add? We should add that W1 and W2 should be orthogonal. So they are not the same. Otherwise, you will get another time, you will get W1 again. So in that case, because W2 also is, because this is 1 by D, so in that case, yes. So W2, as is shown here. So the second that what we need to do, that W2 transpose times W1 must be 0. Or it is the same, of course, if you say W1 transpose times W2 equal to 0, because they you can apply the transpose for the whole of them. So this should be 0. This should be 0. All eigenvectors of the matrix are orthogonal. So by including this constraint, we guarantee that we don't get the same result like W1. So now we will have W2 again. And solving this, it is the same concept as we did before. We just differentiate them with respect to W2. And then when we find what we obtain now that Z W2 equal to alpha W2. Okay. What it means? It means that alpha is the second eigenvalue. And what is W2? W2 should be also the second highest eigenvector associated with, the eigenvector associated with the second highest eigenvalue. This is W2. Okay? And so on. So we repeat the same process for the third time, for the third component, principal component, W3, for the W3T, we should have the variance of Z3 is equal to W3 transpose, and then W3 is equal to 1, and W3 transpose times W2 should be 0, and W3 transpose times W1 should be also 0. And we solve this again, so we obtain the solution will be the same actually. W3 should be the third highest or the third eigenvector, which is associated with the third highest eigenvalue. I will show one example before I continue. I just to give you that what I'm doing here. Here's the octave. So let us assume that you have this data. Okay, so your data is random data. Let's say it is 10. So we have 10 elements. The number of rows 10, but we have, let's say, five features. Okay, so it becomes like this. So we have 10 elements and 5 features. And let us add repeat one of them. But before that, let us just check how to build the covariance. You can check in Octave. You can check the size of any matrix, like size of X. So it gives you 10 by 5. It means that 10 rows and 5 columns. Okay. Now, if we say that Z equal to covariance of X. Okay. Now, what you get? You will get 5 by 5 covariance matrix. This is the covariance matrix of X. So if you can just check size of Z is 5 by 5. Okay. Now, if we like to compute the covariance, the eigenvalues and eigenvectors. So if I said that A and B equal to eigen of Z, yeah, yes. So now, what is here? A is matrix contains eigenvectors. So this is the eigenvector 1, eigenvector 2, eigenvector 3, eigenvector 4, and eigenvector 5. Okay. Those are the diagonal element are the eigenvalues. So this is eigenvalue 1, eigenvalue 2, eigenvalue 3, 4, 5. The larger eigenvalue means more information. If you look to this one, now this is the highest value is 1.284. So the fifth eigenvalue is the highest one. It means that W1 is this one. W1 is the fifth eigenvector. Is the fifth eigenvector. Okay, so we should take this one. And what is the second eigenvector? vector that we should take. We looked where is the second highest eigenvalue, this one, 1.17. The second eigenvector is this one, okay? And you might take also this one, so it means that you take the third eigenvector, okay? Now, if I want to take only these three eigenvectors, then I can build my W, this is W, equal to the matrix A, which contains all eigenvectors of the covariance, but I don't want to take all of them. I would like to take only the third, fourth, and fifth. Okay, so I will take all rows, but for the columns, I will take from 3 to 5. That's all. Now I built the eigen vectors of this matrix. Okay. Now if you multiply, let's say W transpose, okay, times data. What data is X? Size of W is 5 by 3, and size of X, when you multiply, you should check that, yeah. So we should multiply X, yes, X by W, or W transpose by X transpose. It is the same. If you multiply them, now what we have the 10, the same, it is 10 elements, but now we have only 3 columns. We have projected like 10 by 5 into 10 by 3. Now, this new vector, or this new matrix, should contain very close information as the original one, because we ignored only 0.49 and 0.13. Sometimes, let us check this. What happens if I take the same as X, but I will add, I will repeat, let me repeat the same, maybe first vector, this vector, the first one, I will repeat it in the data. So now I take, for example, X capital equal to X is 10 by 5, but I will repeat the first one to the data. So now you can see what happened. The first one, this vector, has been repeated here. So just repetition, just direct repetition. Or we can make it even a little bit more complicated. So not that complicated, but we multiply by 10. Okay. Okay. Now let us do the same. The eigenvector, how it will, what will happen now? We can build the covariance again, but for X capital now. Okay. And we can also calculate the eigenvectors, A and B, eigenvectors of Z. Okay. What you obtain here? You can see the first eigen value is 0. Something times 10 to the power minus 16. It is 0. So it has detected that one of our data is just a repetition of data. Just a repetition. So it has been detected now. It has detected that one of our data is just a repetition. So there is highly linear correlation in our data, which means that I can remove this first column of the eigenvector, so I can use them. So I can remove this eigenvector, and I take the eigenvectors from 4 up to 5, and then I don't remove any, or I don't lose any information. So I can reduce from 6 dimension into 5 dimension without losing any information, because this was detected by that we have 0 eigenvalue here. Also, this one actually is 0.1, so it is very small eigenvalue, which means that it might be possible also to remove one more dimension. Actually, this is it becomes our indication. So this is the calculation, how to do it. Okay. Let's do it this way. Yeah. So we can see here that this is our now new data size. It is W transpose. This is the W capital is the matrix of all eigenvectors that we have calculated based on this principle. So the principle is there. So first, I will repeat it in fast way. So first we build the covariance of data in the same way that we did before. So we have data, so we take the covariance of the data that we have. Once we build the covariance of our data, then we calculate the eigenvalues and eigenvectors. Then we select the set of highest eigenvalues, and then we look to the associated eigenvectors with those eigenvalues, and then we build our matrix W capital, which contains all eigenvectors, contains the interested dimension. And here we just subtract the mean, because we assume that it is zero mean, the data, so we can subtract the mean. But if you leave it, it works as well. So, but here, because in the covariance we assume that it is zero mean. Okay, and yes, that's all. The principle how to build the principal component analysis. There are different techniques to find the eigenvalues and eigenvectors, but the simplest one is to use the packages that we have. But we have singular value decomposition and we have eigen decomposition, but fortunately that you don't need to do them by hand. So we have already some ready package that they calculated. Okay, let us do it over this simple example. So we have here this 3 dimensions, 1, 2, minus 2, minus 1, 1, minus 2, and so on. And this is a symbol and a way of data, or simple table of data. And we like to check how to use the principal component analysis to reduce the size of these dimensions. Here we have 1, 2, 3, 4, 5. We have 5 samples and we have 3 dimensions. Remember that in the principal component analysis, we are looking to reduce the number of dimensions. We are looking to reduce the number of dimensions. It can be modified also to reduce the number of samples. The number of samples, as we will see later. But in general, that we are looking to reduce the number of dimensions, not the number of samples. Okay. Yes. So actually, it is the same as I did in Octave here. So this is our data. I wrote them in as X, and then I took the covariance of Y. Okay. So I call it Y. So this is the covariance. Then we calculated the eigenvalue. When I calculate the eigenvalue, you can see that the first eigenvector is almost 0. This something number multiplied in 10 to the power minus 15, which means that practically it is 0. And then we have 2 large values, eigenvalues. So it means that we can ignore the first eigenvector and we take only the second and the third eigenvector. Okay. So next, what we do, we take we build this W as the second and the third eigenvectors, and then we build then our new data. Our new data now Z equal to W transpose times X transpose minus its mean, and then Z transpose. Now this is our new data set. This is our new data set. So it is the same data, but now we have 2 dimensions. And actually, those 2-dimensional data, it has all information of the original data. So we don't lose anything here. This is the same, but here we have 3 dimensions. Here we have 2 dimensions with all information. Why it is all information? As I said, because I removed only the one which has 0 variance, or also 0 eigenvalue. 0 eigenvalue. In that sense, I didn't lose any information. Okay. If you remove also the second eigenvalue, because it looks much smaller than the third one, because the third one is 21, the eigenvalue. Here it is only 2.6. So if you decide to remove this one also, you will lose some information. You will lose some information, but still the highest information is still there. The highest information is still there, and now you will have only one dimensions. Okay, now what happens if you have a new data set? So we have one new data, 115. We should project them into these two dimensions. Simply you multiply them by W. By multiplying, first you subtract the mean of this data, 115. The mean is 5 plus 1 plus 1 divided by 3, so it is 7 by 3. So I subtract 7 by 3 from all data, and then I multiply them by the new vector, or the new matrix W. Then we have this new data set. A new data set, which means that the projection from 3 dimension into 2 dimensions. This is, by the way, very simple example, because only 3 to 2. But many times you might have like 200 dimension, and you project them only into like 10 dimension or 12 dimension, which makes it much easier to solve. Actually, this PCA, the principal component analysis, it is also used to clean data before you apply the machine learning. Once you have like a big data from database, you and all the contents are in numbers, numeric input, then they apply the PCA in order to clean and to remove any redundancy from your data. There's one example here. It is given on model. You have data part 5. There is 200 samples in the and the 12 dimensions in that file. If you downloaded this data, and then you made the same as we showed now, that you take the covariance, and then the covariance will be 12 by 12 dimension, and then you take the eigenvalue, and you will find that the eigenvalues will be those numbers: 6.1, 4.3, 3.35, 1.64, and then small eigen values 0.35, 0.33, and then you have 1, 2, 3, 4, 5, 6 zeros. 6 zeros. If you decided to remove these those 6 zeros, it means that you take only the highest eigenvectors associated with these eigenvalues. Then you can reduce the data from 12 dimension into 6 dimension without losing any information. All information are still saved in these 6 dimensions. But you can also remove this one and this one because they are very small. So there might be, because of noise, those small numbers. So it is possible also in some application to remove them. So if you remove also this 0.33 and 0.35, then you will have only 4 dimensions. From a 12 dimension, you reduce into 4 dimension. But remember, I repeat one thing, because I remember in one exam, for those who come to take the exam of machine learning, one student they made some students they made some mistake here. For example, when they have so assume that you have x1, x2, x3, x4, x5, and x6, for example, and you have maybe 100 elements. So they did very well. In the beginning, they compute this covariance matrix correctly, which is dimension is 6 by 6. They take the eigenvalue correctly. They compute the eigenvalues. They found the eigenvalues, for example, let's say 5, 7, 3, maybe 0, 0, 0. So they knew that they should remove these, because the dimension can be projected from 6 to 3 dimensions without taking into account or removing 3 dimensions, and in that case, they without losing any information. Then they build correctly also W. So W contains W1 vector, W2, and W3. W1 is the eigenvector associated with 5, W2 is the eigenvector associated with 7, W3 is the eigenvector associated with 3, or you can, of course, sort them to be like starting from the maximum, for example. Everything is fine. But when they come to apply, they made big mistake. What they did, they said that, okay, the last 3, they don't have information, so they removed those. They removed those. This is a very big mistake. because this is not like feature selection here. You cannot remove any vector, okay? But what to do? You should multiply all this by the new W, then the result will be 3 by 100. So now we have 6 by 100. The element is 6 by 100, 6 like columns and 100 row. The result will be 3 columns. So we have Z1, Z2, Z3, and then we have 100 inputs. So this is the projection. So we have projected this data into lower dimension. But we cannot just remove, we can't remove just one of those features. Okay? So this is very important to remember. So the principal component analysis doesn't remove like one feature or two features, but they project them. They project them in lower dimension. So this is very important to remember. Yes. There is one thing, for example, if you want to remove only the zeros eigenvectors, or sorry, zeros eigenvalues, it is not always possible, or in practice actually, it is very rare to find zeros in the eigenvalues. You might have small numbers, but not zeros. How to select the threshold to say that, okay, I will remove all these eigenvalues that less than this number? One method is by using, you remove the eigenvalues which is less than or equal to, for example, the average eigenvalue. The average eigenvalue. So the average eigenvalue, it can be computed as the trace of the covariance matrix, because if you have any matrix, let's say you have this matrix, covariance matrix like 5, 2, 1, 1. Of course, it should be symmetric in this case, okay, and 7, and maybe 3, and then we have 3, and 1, and 10, okay. And just example, so the trace of A is the summation of the diagonal. So it is 5 plus 7 plus 10. And actually the trace of any matrix, when you take the summation of the diagonal, is the same as the summation of the eigenvectors. It is the same as the summation of the eigenvectors. So you take the summation of the diagonal element and you divide by 3. So this will be the average eigenvalue. So one method that they take this average eigenvalue as a threshold. So they consider only eigenvalues which is higher than the average. This is one method. But of course, if you are like if the application is conservative application, so every piece of information is important, in that case we should select this threshold to be as low as possible, as small as possible. Because as you increase the threshold, then you lose more information from your input, or from your data. Okay. Remember that if our data originally is normal distributed, then also when you make the projection, the result from the projection is also normal distribution. So because normal distribution will not be changed after the linear projection, so it will be also like normal distribution. Okay, here is just a simple extension for the problem that if we want to look also to the it is called feature embedding. So sometimes that we have already small number of dimensions, but we have much larger number of samples. So it is possible also to reduce looking to the repetition or the redundancy in the samples itself, not in the dimension. So it is possible also by simple extension of the PCA, sorry, the principal component analysis. In that case, it is called feature embedding. but it is also the same concept actually. And when it is applied, sometimes we have, like, let's say we have 50 different samples, and D can be, for example, 10,000 length, like in gene, for example, applications. So in that case, okay, I will explain why we are doing this. We have seen that we need to calculate the covariance matrix. The covariance matrix is D by D, the dimension. Okay, so if you collected data from genes, like genetic, okay, so from genes, that sometimes you have 10,000 length of data. So 10,000, so D can be 10,000. Okay, so now the covariance matrix can be 10,000 by 10,000. So it is very huge, very large. It requires a lot of computation, okay, in order to find eigenvalues or eigenvectors. And sometimes you have the n, the number n is only 50, from 1 to 50, for example. So it is better to work over n instead of working over d by d, to work over n by n. So instead of computing the covariance of the data itself, we are looking to the covariance of the data transpose. And in that case, we will have n by n. How to use them is also, it is shown here, which is also just simple extension of the same problem. Okay. Okay, here is called the multidimensional scaling. So it is quite similar to the PCA, but we don't use Euclidean distance in measuring the neighborhood points. But I will skip this one. The singular value decomposition is also one method that we can apply directly to the data in order to find the eigenvalues and eigenvectors. It is called singular values in that case. Linear discriminant analysis is the same as PCA, but now we take into account also the resultant. So it is supervised data reduction, not unsupervised. It is supervised data reduction, and this will be the topic of the next lecture about how to use. If we know that, for example, this belongs to class 1, this belongs to class 2, this belongs to class 1. If we know the result of the data, how this could be used in order to reduce the data size. Okay, that's all for today. Thanks a lot.